episode 2 of AU Manufacturing Conversations with Brent Bilinsky. This time around we're speaking to Henry Bilinsky, no relation, the founder and CEO of MicroTau. Henry founded his company in 2016 after proposing an approach he calls Nature's 3D printer in response to a US Air Force challenge to reduce fuel use for transport aircraft. Out of nearly 300 entries, his idea to improve fuel efficiency, which creates a surface like shark skin for the outside of a plane, made the final 10. Then it was one of only 3 from those awarded proof of concept funding to go further. MicroTau has been quietly refining its technology since through developmental grants from the US Air Force and others, and last month completed a seed fund round of $5.6 million led by the Clean Energy Finance Corporation. Henry tells us about the science behind making a surface rougher to go faster, progress so far, how their new spin on photopolymer 3D printing can borrow from bugs and animals, the path to certification, and more. A tiny note here to apologise for a couple of stray noises on the recording. 2 episodes in and I've learned that it's wise to turn off phone notifications when the tape's rolling. We hope you enjoy this episode, and we've got a ton more in the pipeline. Subscribe wherever you get your podcasts, get on our newsletter mailing list, follow us on all the usual social media channels, and tell your friends. Now here's Henry Bilinsky on AU Manufacturing Conversations. Henry Bilinsky, my near namesake, thank you very much for joining us on AU Manufacturing Conversations.
Thank you for having me.
So tell us about yourself, Henry. How did you get here and what do you make?
So I'm the CEO and founder of MicroTau, where we print nature's surfaces to solve human problems. We have an advanced manufacturing technology which is similar to certain kinds of 3D printing, so liquid resin or photopolymer-based 3D printing, which allows us to print these microscopic patterns that you find on plants and animals that provide useful functional properties. So things like shark skin, which is our main focus, which if you've ever touched a shark, you know it feels like sandpaper because there are microscopic ridges on the surface of the shark. Shark evolved those in order to become a more efficient hunter. So these structures have the effect of reducing friction drag. And so by replicating those structures, we're not harming any sharks in the process. We're just copying the microscopic ridges that are spaced on the order of about 50 micron apart, or half the width of human hair. And we put that on aircraft and ships to reduce drag, save fuel, and decrease carbon emissions.
So I'd like to sort of stay with decreasing friction drag for a bit. I knew nothing of riblets, heard of them via what you're doing, and I thought to begin with the idea of making a surface rough so an object it's attached to can travel more smoothly through the air or water, it seemed a bit weird to me. How does this concept work, please?
So you're exactly right. Usually smoother is better when it comes to drag. So you typically want to say polish down a surface to make it extra smooth. The reason that these riblet structures, as they're known, so these microscopic ridges called riblets, the reason that they reduce drag is because, first of all, they function in turbulent flow. So when you have flow of a fluid, say air or water, it'll most of the time be turbulent flows. So laminar flows when you've got very organized, smooth sort of layers of liquid or fluid moving over a surface, and then that will transition into messy flow or turbulent flow, which is chaotic and produces a lot more drag. Sort of think of it as like, say, a smooth running stream would be laminar flow, and then once you get to whitewash or white water, that's when it's looking more turbulent.
Mm-hmm.
So in turbulent flow, you've got a whole mess of stuff going on, but you can, there's a phenomena that predictably occurs in turbulent flow of these microscopic vortices, so like a little spinning of the fluid, called hairpin vortices, roughly on the order of the size of a hair, which is related to the hair size that I talked about before. Yep. And that's producing more scrubbing and more friction on the surface. So if you can make these ridges, these riblet structures, just narrower than the diameter of those hairpin vortices, and the diameter of those vortices is very predictable based on the flow conditions, specifically the wall shear, then even though you're making the surface more rough, which again, counterintuitive, but even in spite of the fact that you're increasing the surface area, you're making it more rough, you're excluding those vortices from the surface because they can't fit in between those riblet or microscopic ridges. So what you end up with is kind of an enforced little laminar layer in the boundary layer, and that scrubbing of the vortices only happens on the top of these very sharp ridges. So the net effect is you reduce your friction drag by about 8%, although we're trying to get that to a larger number.
So again, to stay with riblets and my lack of knowledge with them, I had a look around because that's what you do when you hear of something the first time, and I saw that NASA have been in the riblet game since the 1970s, and they've even made some riblets to go to onto the yacht that won the America's Cup back from Australia. And then I looked a little further and I saw BASF and 3M and some researchers from Germany's Fraunhofer were also on the case. What's different from your approach compared to some of these others?
Yeah, so definitely riblets. Sharks have known about riblets for even longer, but NASA originally did the work, 40 odd years ago. So I guess what the current state of the art is compared to that work back done, like you referred to with the America's Cup. The issues there were that you had a manufacturing process that was only able to make these sort of more triangular shaped riblets, which had less drag reduction ability. You sort of want to make them more tall and sharp to get a better drag reduction effect. As well as that manufacturing process meant that you had a thicker material. So when you're looking at applications like in aviation, you were adding more weight. But critically, the materials as well were not durable enough. So when they're exposed to the high intensity ultraviolet light that an aircraft experiences at altitude, resulted in degradation of material, yellowing, cracking, microfracturing, and it basically degraded the material and then was really slow and expensive to remove because you have these little shards of material.
Yep. So
since then, a lot of work has been done in a number of different aspects. So on the materials front, so what you refer to with BASF or the Fraunhofer Institute, the BASF product, which is done in collaboration with Lufthansa Technik, called AeroShark, looks as though it's got a much better material. So the materials, we're all beneficiaries of the fact that materials development, especially in, say, photopolymer materials, which is what we manufacture out of, have improved significantly in the intervening decades. And so they've got material that's flown on a 747. They're looking to certify that on further aircraft. I believe it's a 777 next. How we are distinct from that product and that manufacturing process is coming down to the manufacturing process. So our understanding is that is made with what's called nano imprint lithography, which is effectively a stamping process where you get the negative of the riblet structures you want to make, you push them into a UV curable coating or a photopolymer material, and then you cure it and remove that stamp to leave the imprint on the UV curable coating. Where we're distinct, so our process we call direct contactless microfabrication, or DCM, is a contactless process where we put down the same kind of material, so also a photopolymer material or a UV curable coating. I apologize, I'm sort of using those terms interchangeably. They kind of depend on who you're talking to. We say UV curable coating, so I'll stick with that. So we put down that coating, and then we have an optical system that projects the desired microscopic riblet pattern into the surface. So that then traverses across the coating and only cures where the light hits it. And it actually grows these riblets within the coating. So the reason why that's distinct and quite different to the typical approaches that are taken, say, like nanoimprint lithography or stamping processes, is that we can change the designs very readily. So the fact that I say that we grow the structures within the coating means that we can actually change the 3D topology by adjusting the light field and the printing parameters. So we have a nominal tooling process to change designs. In the context of nanoimprint lithography, you have very high costs to manufacture the negative stamp that you're using to do the imprinting. So you're typically talking 5 figures or more to change any design once. So we have a lot more design freedom in that respect. The reason why that's important, especially in the context of riblets, is you want to optimize the spacing and the size of those riblets to your local flow conditions to get the best benefit. So we're already orders of magnitude cheaper in terms of being able to change those designs. We also have more design freedom. So because we're not a contact process, we don't have to worry about things like high aspect ratios, which can cause issues with your stamping, or making more complex three-dimensional designs, which I sort of referred to before. We're hoping to get even more drag reduction by testing new, more exotic designs. So we're in a position where we can do that. I would say we're we can do that. It's sort of prohibitively expensive when you need to retool a stamp every single time at significant cost with alternative manufacturing methods. And then the final piece is that we have a very scalable process because there's no contact. It's just essentially light moving across the surface. We aren't at this scale yet, but one of our devices at scale could be printing on the order of hundreds of square meters a minute, just because the light moves across the surface and the curing reaction happens very, very quickly. So all of those things together are a very long-winded answer to say that we can make a product which reduces drag more, so saves more fuel or saves more carbon emissions, as well as has lower costs, so lower cost to manufacture, as well as having a less material on the surface as well. We can have a lighter product, which also improves your performance.
And so you mentioned some of the improvements in some of the riblet materials over the years. Though I'm sort of still curious about, you're making tiny features that go on stickers, and then the stickers go on the outside of something that's literally flying through the air. And, I'm curious about what you need to do to make that strong enough on the job and not, disintegrate somewhere at very high altitudes.
Yeah, so we actually first started thinking that we could take existing UV curable coatings used in aerospace and just to use our process to microstructure the surface. And so we'd get to leverage materials that have already qualified in aviation. However, we found when you form into those microscopic patterns, the mechanical properties are very different. So something which might be very robust if you cure it flat. If it's very sort of rigid, if you have these microscopic ridges, then under impact or abrasion, they can scratch and snap and break off. So we have actually we've been doing this for a while now. We develop our own materials, which were more specifically suited to being these microscopic patterns. So in order to make sure that they're going to survive in an aircraft, there's a couple of things. One is the material itself. We take through, we're working with a aviation original equipment manufacturer who has a set of material specifications that say, if you pass all of these laboratory tests that effectively simulate what an aircraft will go through over its maintenance life cycle, then we say that should survive in flight and in service. So these are things like mechanical durability testing, chemical, and weathering resistance. So that's one piece of it. And effectively, there are coatings that have already survived those kinds of tests, and then we've just sort of got these additional mechanical properties that we've introduced by being a bit tricky with our formulation. The other thing you mentioned is about, if this is a film that we're sticking onto an aircraft, how do you make sure it doesn't fly off, which you definitely don't want to happen. We're also working in the same respect to these material specifications that are used for aviation wraps or decals. So if you've seen an aircraft with, say, an ad for a band or a footy game on the side, that's typically not painted on, but it's actually film that's been stuck on, similar to like a vinyl wrap on a car. And there are specific pull-off adhesion strength tests, which say this is going to be able to make sure that it stays on the aircraft, it's not going to fly off in service, but also can be removed afterwards, which is an important part of the process too.
And you also, one of the things you mentioned earlier was the flexibility of your approach. And, you're not just looking at shark riblets, you're looking at some other biomimicry concepts, your website says. Examples were around antibacterial surfaces and ones that can self-clean, all very interesting, of course. What are you borrowing from nature, and how do you express this through your DCM process?
So there's a whole field of biomimicry or biomimetic surfaces, so copying nature. And a lot of very smart people in academic research have looked into these different surfaces, like the ones that you mentioned. There's also things like adhesive gecko pads or anti-reflective moth eyes, namid beetles that are these desert beetles can actually harvest water from the desert air. Essentially, by inspecting these fascinating properties, looking at them under a microscope or an electron microscope and seeing what the surface topology looks like, then replicating those structures and seeing that you can get those same properties is where a lot of that work has happened initially. But they're using sort of very non-scalable and expensive processes to make that happen. And so we're looking at our current capabilities and working out how we can copy those structures to produce useful, valuable properties. Our main focus now really is on the shark skin effect, but we have had a few research projects with some research institutions here in Australia. I say here in Australia, I'm not currently in Australia, but where we are in Australia. So things like we've made some surfaces that have prevented biofilm migration, so for medical device applications or some of these self-cleaning surfaces. However, at the moment, we really are focused on kind of our headline mission at the moment is to reduce the 300 odd billion that commercial aviation shipping spend a year on fuel and the almost 2 billion tons of carbon they do producing the process.
Well, besides you being in another country, one of the reasons we're not speaking face-to-face is that your factory is in beautiful Sydenham and right under the flight path and therefore very noisy and not amenable to recording. Tell me about the proximity to the airport. Is that something that features into your R&D, or is it just a neighbourhood you happen to like?
I would love to say that it was a big strategic choice to go there for the airport. It has been handy in terms of international travel when we're allowed to travel internationally, as well as having proximity to, say, Qantas's jet base and going to be able to inspect aircraft and understand the logistics of moving around an aircraft and maintenance procedures that go on around them. But no, we picked that spot off. It was the second year of the company. We were looking for some industrial space, and it was a great spot for us. It's also kind of handy because there are sort of a series of industrial units, which means we can kind of grow piecewise, whilst also being reasonably central. We're right on the train line, so it's easy to access.
Right. I imagine, and I'm just guessing here, the proximity to University of Sydney, where you did some early development work, is probably also useful.
Yeah, absolutely. So there's the Australian National Fabrication Facility node at the University of Sydney, where they have basically the Sydney Nano Institute, which is this incredible sort of world-class facility with clean rooms and sort of chip manufacturing type capabilities. And we've worked with them since almost day zero to get specialized and custom components made, which go into our manufacturing process. Being able to order that and quickly hop over and pick it up is a lot easier than navigating some far off unknown manufacturer in another country.
What's the current size of your team, and what are some of the scientific and engineering and other disciplines that make the magic happen?
Yeah, so at the moment we have about 12 people full-time and another couple part and contracting, but we're very much growing. So we've just recently done an investment, our first institutional capital raise, which means that we're growing the team. But in terms of where we're currently at, we've got materials chemists on board for doing our materials development work, engineers across aerodynamics, mechatronics, effectively to build what we call our printing systems. Optical engineering is another key part because we print with light. Being able to produce that microscopic light field is a key part of the process, as well as more chemistry and physics expertise on board. We've also got a nanotechnology specialist who came over from the Sydney Nano Institute, who's been a great add to the team.
And so congratulations, of course, on your recent seed round closing. Nice to see high-tech manufacturers getting backing. I saw that you'd mainly been bootstrapped up until that point. How did you manage that for something that I imagine takes all sorts of expensive equipment as well as qualified and therefore expensive people?
Yeah, so we were lucky in that when I started the company in 2016, it was off the back of winning a contract with the US Air Force Research Laboratory. So that actually is what sort of started the company. There was an open innovation challenge posted at the end of the previous year, 2015, looking for ways to save fuel on their legacy transport aircraft. And so we won that contract. So we had revenue from day one. And then from the success of the first contract, we've won subsequent contracts, 5 to date, and we've got some more coming in the pipeline. So we've won a number of these sort of development type contracts where we're developing our tech or product for a given application, as well as we've won a number of competitive grants in Australia. So things like Accelerating Commercialization Grant with the federal government or the New South Wales Physical Sciences Fund have been hugely helpful in supporting the work that we do. But yes, now we've sort of definitely with the capital raise, we have a much larger chunk of capital to deploy to really push ahead and get this flying.
Next, I'd like to learn about your path to commercialization. What needs to happen before a customer gets certification to fly with some of your film on the outside of their plane, and then you are presumably making tons of the stuff for them?
Yes, so there's a few key things that we're going to be achieving over the next period with this money in the bank. So one is we actually have already done our first flight test. We did that on a racing aircraft late last year. A pilot called Matt Hall is the Red Bull Air Race World Champion. So we are able to fly on unregulated aircraft or experimental aircraft, things like racing planes or unmanned air vehicles, and we intend to keep pursuing that work in order to learn more, develop and optimize the product, as well as get key data and demonstration for our ultimate commercial airline customers. We need to qualify our product from a materials perspective. So I referred to before working with an OEM on a material specification. We want to make sure we pass all those tests so we know that the material from a durability perspective is good to go. We need to scale up our manufacturing. So the facility in Sydenham, as you mentioned, we're sort of doing orders on the order of about 10 square meters currently. So that's enough for small aircraft. But for our first commercial aircraft flight test, we need to be on the order of about 400 square meters. So we'll be scaling up our manufacturing for that, as well as de-risking and demonstrating the real scale up, which is more on the order of tens of thousands of square meters when we have this across the commercial aviation fleet. Then there is the certification arm. So CASA in Australia, the Civil Aviation Safety Authority. It's a matter of submitting a flight certification plan to get what's called a supplemental type certificate. So a type certificate is a type of aircraft that's been certified with a given aviation authority and is allowed to fly. So it could be a specific 777. And then we submit what our certification flight plan is to CASA, and then they would come back with any notes or adjustments. They can be a back and forth. But then for us to have the approval of, okay, if you complete this flight certification plan, then you'll get your supplemental type certificate. So we are planning to have everything in place in terms of a product that's ready to go and the manufacturing capacity to do so, and the flight test plan certified and all lined up and ready to go with our first launch customer in commercial aviation, to have all of that in place to then undertake the certification testing in about 18, 24 months. So you won't be sitting on a commercial aircraft flying with our shark skin on it until after that.
You mentioned the competition, the open innovation competition that was part of the invention of what you're working with, and I've seen other manufacturers who've their genesis is in university competitions. I can think of a couple that are leading the world in the automotive industry at the moment that got their start in that fashion. We can think of examples like the DARPA Grand Challenge and the X Prize, where really capable and sometimes non-traditional teams have developed amazing technology and have been driven to do so by a prize. What's your view of a competition as a way to drive innovation, and do we need more of them in Australia?
So I think they're fantastic. I think if nothing else, they're really entertaining to get involved in. You get to learn about challenges and problems that you may not necessarily be familiar with, and they are explicitly designed to find, as you said, non-traditional contractors or partners or people who could be submitting these ideas. So I think I would certainly say more is better, and we would not exist were it not for this open innovation challenge that was put forward by the US Air Force Research Laboratory. But yeah, I think they're fantastic. I think there's probably a lot of work for the people who are pulling that together, in terms of they've got to then go through and sort the different answers and dig into them further. But I think the benefits can be great, and certainly as the beneficiary of one of these competitions, I think they're fantastic. The opportunity that we got, we wouldn't have had otherwise.
And so last few questions. One of them I like to ask guests because the answer is always different, and the answer is always, well, more importantly, just fascinating. Why is it important that Australia develops its manufacturing capacity? Why do we need to be, as they say, a country that makes things and more specifically, that can make complex things like what you're doing?
I think high value manufacturing is certainly where Australia's future should be lying. I think we can leverage the very smart and skilled workforce that we have here to be able to do that manufacturing. So to not necessarily just take resources that we may have here and have them be processed elsewhere. I think we'd be in a much stronger position to capture more of that value chain here in Australia. I think there's a lot of big changes happening globally at the moment. There's a lot of push for our transition to a more renewable economy, and I think Australia is particularly well placed to take advantage of that. And I think we should be doing everything in our power to make it happen. I think it's a win on many fronts and a much more long-term sustainable economic opportunity for Australia. I'm happy that we're playing a small partner, but I think there's a lot more happening outside of what MicroTau does, and I think there's a great opportunity for the country.
And lastly, is there anything you'd like to plug while we have you on the line?
Oh, you put me on the spot. Sorry, I'm still waking up early in Europe.
My apologies.
No, I should have picked this ahead of time. I think we right now we're growing the team. We're looking for new talent, and so if anyone is interested in joining, whether it's in a technical or non-technical role, please go and hop onto our website microtau.com.au and have a poke around to see if there's anything that fits, because we're keen to have good new talent to come and grow the team. And then I guess if there are a particular, specifically unregulated aircraft operators or manufacturers who would like to see our product flying on their platform sooner, we're always keen to have a chat and see if we can get you some extra performance or some fuel savings or reducing your carbon footprint.
Well, Dr. Bilinsky, it's been a pleasure to speak to you, and I really appreciate you making the time.
Thank you very much.